In this set of slides, we're going to discuss another example of least squares adjustment. In this example, we are dealing with trilateration. We are doing an adjustment of a trilateration at work. Trilateration is a method in which we can determine coordinates of points based on measurements of distances only. So we, in this example, have this quadrilateral. It's basically the measurement of two triangles, and or three triangles, a number of triangles. Anyway, we have the measurement of distances between these 4 points, A, B, C, and D, as shown in the figure. We have the control points. Points A and B have known coordinates, and we have measured 5 distances, and each distance, L1 to L5, was measured 6 times. So we have 30 observations, n equals to 30. And we are dealing here with a two-dimensional problem, so we're dealing just with the x, y coordinates. X is would be easting, and y would be northing. And which means that the unknowns are coordinates of C and D, X, Y. So we have 4 unknowns. We are going to consider that the observations have a covariance matrix. The covariance matrix is going to be built by means of the known specification of the instrument. I believe we are using 2 centimeters plus or minus 2 ppm, something like that. You're going to have that given to you, because we're going to work on that. That's going to be assignment number 1, by the way. So the a priori variance factor we are going to consider as known and equal to 1. And for the adjustment, of course, we will need the approximate values for points C and D. Okay, that's an input into the adjustment. This is clearly a parametric model in which the observations are a function of the unknowns, and the unknowns are basically the distance as computed by the coordinates, as a function of the coordinates. The design matrix we have to form. The design matrix. Let me just try to write something here. Is this thing here? Yeah. So this is the parametric equation that we're going to use. This is the nonlinear model, and what we need in here to solve for the 4 parameters, the least squares correction vector to the coordinates x, y, c, x, y, d, are the design matrix, the weight matrix. That's the inverse of the covariance matrix. We're going to form the covariance matrix based on the specifications of the EDM, and the other array is the misclosure vector. So how do we form the design matrix? We know the design matrix is composed of partial derivatives of the mathematical model with respect to the parameters. So here we have the mathematical model written for the first row of the matrix A, and this is basically what? The difference between the observations and the geometric distance, the distance that we form based on the coordinates, the station coordinates. So this is observation, this is model. Okay, so it satisfies here observation, model. And so we are going to have to evaluate the each element of the design matrix the design matrix has dimension 30 by 4. Okay, 30 by 4 because we have 30 observations and we have u equals to 4 unknowns. So 30 rows, 4 columns. What else? Okay, the misclosure vector. Look at here, the misclosure vector. It has been written to satisfy the mathematical model. Okay, we wrote the mathematical model as L minus Fx. Okay, so the misclosure vector follows the same, has to satisfy that. That's very important. Okay, we cannot write the misclosure vector, write the mathematical model L minus Fx, and then use the misclosure vector Fx minus L. It's going to it's going to collapse. We're not going to have it's wrong. It's wrong. Basically, it's wrong. Okay, we have to be consistent. So let's discuss how we can get the approximate values for these points C and D. At the approximate coordinates for points C and D, this is a 2D problem. We may either be on the mapping plane or a topographical plane, doesn't matter. We're going to be using just the well-known coordinates to solve for the direct problem on the 2D plane. You know this very well already. The coordinate of a point, for example, x of D, is the coordinate of the known point xa plus the distance multiplying the azimuth between A and D. And so we have to do that for points x and for points D and C. Here I'm following this order. The knot here represents approximate value. So what we have in here is we need the azimuth from A and D. We have the coordinates of points A and B. Okay, therefore the azimuth AB is known. We can compute from the coordinates. Okay, the tangent of delta y over delta x, or delta x over delta y. And so what we need to obtain the azimuth from A to D is this angle here, the angle between from B centered at A towards D, alpha BAD, the alpha bad. So and how we compute this angle here, this azimuth, we have this azimuth AB, this angle we are going to compute based on the law of cosines. Okay, so we need to this solution, we need to know the distances, the sides of the triangle, and we are going to compute the internal angle of the triangle. And we can do the same for delta C. Of course, the geometry is going to look differently, and you can go and work that yourselves. Something that is of practical importance is this thing here. It is wise to use all observations, and then you take their mean value to avoid existing blunders. So we know that each one of these observations, so observation L1, for example, was measured, 6 times? And so let's suppose that one of these observations has a blunder, that is a mistake, an error in the observation that was not detected. So if you just pick up one value randomly, you may pick up the wrong value. Okay, well, not the wrong observation, but the observation with an error. And so to avoid that, we can take the mean. Okay, because these, if there is any error, the error is going to be minimized. Okay, let's look at design matrix. So here is the design matrix, how it looks like. As we talked, the design matrix is 30 by 4. Okay, so here we have the 4 columns. Each column here is basically dealing with one particular coordinate value. They wanted money. Okay, so we have the coordinates. This is point D, and the coordinate Y for point D. Okay, this is the order that I'm building the design matrix. And again, it is consistent with the least squares solution vector. Okay, and each row represents, corresponds to one observation. Observation L1, observation L2, observation L3, etc. Observation L30. Okay, so the partial derivative of the distance model is always the component delta x or delta y divided by the geometric distance. This is the geometric distance here. And of course, the geometric distance is evaluated by means of the approximate value of the coordinates. Okay, so that's the design matrix. This is the misclosure vector. The misclosure vector will be composed by making the difference between each observation and its corresponding geometric distance. The adjustment of a trilateration network is usually used as assignment. The data sets will be made available to you. Before ending, I would like to make a comment that is very important. In this example, we are treating the coordinates of the control points as errorless. We are disregarding their uncertainties. Okay, we're basically ignoring their standard deviations. This is not a best approach. This is common, I have to tell you, it's common in surveying, but it is not the best approach. I will call that unrealistic. A better approach is when we take into account the uncertainties of the known points. This is what we call adjustment with weighted constraints, and that's going to be a subject that we're going to discuss in the near future. It's important to realize that the same example of trilateration network will be dealt with in the context of adjustment with weighted constraints. Okay, so that's all. Have fun and see you later.